Have you ever wondered what it actually takes to build life from the ground up? Well, today, we're going to step into the world's tiniest kitchen and uncover the fundamental recipe for life itself, what it really takes to create a microbe from scratch.
So what's the secret sauce? What's in the cookbook for these microscopic powerhouses? What do they need to eat? And what kind of environment do they need to not just survive, but to actually thrive? That's what we're digging into today.
And the key to this whole recipe, the thing that makes it all work, really starts with understanding the engine that drives them. And that engine is their metabolism. It's how they turn all those basic ingredients into life.
Okay, let's dive right in. First up, let's get a handle on why. Why do microbes even need a recipe in the first place? What's the point? Well, a microbe's life is this constant balancing act. It's a tug of war between two different modes. On one side, you've got anabolism. Think of this as the cell's construction crew. It takes simple nutrients and energy to build all the complex stuff the cell needs. And on the other side, you have catabolism. This is the demolition crew. It smashes up nutrients to release and capture that energy. And to keep this whole cycle running, they need a steady supply of raw materials. Which brings us right to the heart of it all. Section 2, the ingredients. Let's talk about the microbial diet. What exactly is on the menu? Okay, let's start with the absolute king of the ingredients. A full 50%, half of a cell's dry weight, if you took out all the water, is made of just one thing, carbon. It is, without a doubt, the foundation of everything. So, there it is. Ingredient number 1, carbon. If you think about our recipe like baking a cake, carbon is the flour. It's absolutely essential. It's the structural backbone for pretty much every single organic molecule inside that cell.
So how do they get it? Well, microbes usually take one of two paths. You've got heterotrophs, which are a lot like us actually. They get their carbon by eating other organic stuff. But then you have the autotrophs. These guys are the real master chefs of the microbial world. They build their own food from scratch using inorganic carbon dioxide, just like plants do. All right, our second key ingredient is nitrogen. It's the runner-up, making up about 13% of the cell's weight. And you absolutely cannot live without it. It's crucial for building proteins and, the actual blueprint of life, DNA.
Of course, a cell needs more than just carbon and nitrogen to get by. So let's take a quick look at the rest of the pantry. You need phosphorus for DNA and cell walls, sulfur for important amino acids, potassium to get enzymes working, and magnesium to keep things like ribosomes stable. And for some microbes, especially the ocean dwellers, calcium and sodium are definitely on the shopping list.
But look, these are just the bulk ingredients, the main stuff. And as any good cook will tell you, a great recipe isn't just about the flour and sugar. It's the spices. That's what makes it really special.
And that's where micronutrients come in. These are the spices in our microbial recipe. Iron is a huge one here. It's absolutely critical for producing energy. Then you've got other trace metals like cobalt, copper, and zinc that act as little helpers for all the enzymes. And finally, you have growth factors, things like vitamins that a microbe can't make for itself. They're only needed in tiny amounts, but they are 100% necessary.
All right, so we've gathered all our ingredients. But you can't just leave them on the counter and expect life to just happen. You need the right kitchen. And that brings us to Section 3, the microbial kitchen, aka the conditions for growth.
First up, temperature. And for microbes, it is all about the Goldilocks principle. For every single microbe out there, there's a minimum temperature where it's just too cold, a maximum where it's way too hot, and then there's that sweet spot right in the middle, the optimal temperature, where it grows the fastest. It has to be just right.
So why is temperature such a deal breaker? Well, if it gets too cold, the cell's outer membrane gets all stiff and rigid, kind of like butter you just pulled out of the freezer. Nutrients can't get in anymore. But if it gets too hot, its most important proteins and enzymes literally unravel and stop working. The whole cell just falls apart.
And what's amazing is that microbes have adapted to pretty much every oven setting you can imagine on Earth. You've got your cold-loving psychrophiles, your mesophiles like E. coli that love our body temperature, the heat-loving thermophiles, and then the real extremists, the hyperthermophiles that can live in volcanic vents.
Okay, let's turn another dial in our kitchen, pH. Just like with temperature, every microbe has a very specific range of acidity or alkalinity where it feels most comfortable.
And yep, we've got names for these preferences too. Acidophiles, as you might guess, love acidic conditions. Neutrophils, and this includes most of the microbes that hang out with us, they prefer things neutral.
And alkalophiles, they thrive where it's alkaline or basic.
Now for a hugely important one, water. So picture this, when the world outside a cell gets a lot saltier than the world inside, all the water inside the cell gets pulled out to try and balance things. It's a process called osmosis, and the result? The microbe shrivels up like a raisin.
And it all comes down to this one simple, powerful truth. A dehydrated cell cannot grow. End of story. Without water, all those metabolic processes we talked about just grind to a complete halt. It is absolutely non-negotiable for life. So we have the ingredients, we have the right kitchen conditions. So what's the payoff? Why is knowing all this so important? That brings us to our final section, hacking the recipe for good. And here it is, the big idea. Because we understand this recipe, we can actually change it. By controlling the ingredients and tweaking the conditions in their kitchen, we get the power to control their growth. And we use this recipe hack all the time, often without even thinking about it. When you preserve food with salt or sugar, what are you doing? You're messing with the water availability. When you sterilize medical equipment with high heat, you're cranking that temperature dial way past the maximum. This knowledge is fundamental to everything from food safety in medicine to public health and modern research.
So, we've just walked through the entire recipe for how to create and grow microbial life, which leaves us with one last pretty provocative thought, doesn't it? If this is the recipe to make them grow, what does that tell us about the recipe to stop them? Something to think about. Thanks for joining me.